Okay, in this video I'm going to discuss further follow-up test alternatives after a one-way MANOVA with more than two groups. So in the previous video where I was illustrating running a MANOVA, I discussed one alternative, which was to utilize univariate ANOVAs, which are printed out by default in SPSS as follow-ups to a MANOVA result. So, and then also you could even follow those up theoretically by clicking on various post-hoc test options or running certain planned contrasts. The downside of utilizing those particular strategies is that you end up reanalyzing the same variation again and again in the dependent variables and ignoring their intercorrelations. So in effect, it violates the spirit of the MANOVA that you just carried out. So there are other alternatives as follow-up tests to the MANOVA. And so I'm going to discuss two additional ones. One is to carry out a step-down analysis, and the other is to carry out discriminant analysis. So I'm going to first just kind of replay the basic MANOVA analysis that I was discussing in the previous video, and then illustrate how to go about carrying out the step-down analysis and discriminant analysis. So to carry out the one-way MANOVA, first of all, keep in mind that in this data set I have 52 cases, I have 4 variables. My independent variable is plans, so basically high school students' plans concerning attending college at some point after graduation. So for this variable, it's a nominal variable. We have the values being 1, plan to attend college full-time, 2, plan to attend college part-time, 3, plan not to attend college at all. And then we have academic self-efficacy, perceived utility of college, and intrinsic motivation for learning as my dependent variables, these all being assumed to be continuous. So just kind of replaying the basic MANOVA, I go to Analyze, General Linear Model, to Multivariate. I'll put my independent variable into this box and my dependent variables over into the dependent list box. I can ask for various options, getting grand mean and group means for my levels of for the dependent variables, or the means for my on my dependent variables for my levels of the per level on the independent variable. Excuse me. We have descriptives, effect size, power, homogeneity tests, and so forth. So when we run the basic MANOVA, you'll see you end up with your descriptives with means and standard deviations for each of your dependent variables. So there's self-efficacy, there's perceived utility, and intrinsic motivation. Just kind of scrolling down, you see here's our multivariate test. Keep in mind that in a two-group MANOVA, all this information from the F column all the way over will be exactly the same when you're looking at the effect of the independent variable and the dependent variable. And the reason why is because there's only really one way in which the dependent variables can be combined to produce group separation. And so essentially one discriminating function. So, but in the case where you have more than two groups, then there are more ways in which the dependent variables can be combined to produce group separation. And so that's why you have multiple lenses. Each of these tests provides sort of a different way or a different lens for looking at the effect of the independent variable on the dependent variable. So, just kind of looking at Wilks lambda, for instance, we see that there's our lambda value, and we see that based on this test that we have significant group differences on the set of dependent variables, again, as a function of the independent variable plan. So, and then just kind of scrolling down a little bit more, you'll notice that we have univariate ANOVA follow-up tests. These are the defaults in SPSS. So here you've got, again, plan is our independent variable, self-efficacy, utility, and intrinsic motivation. Each of these are dependent variables, and each of these tests right here are univariate ANOVAs. So comparing group differences on the dependent variable and basically ignoring the intercorrelations that may exist among these three dependent variables. So like I said, the downside of this is that it basically violates the spirit of the MANOVA itself, and you end up reanalyzing the same variation in the dependent variables over and over. So one alternative strategy to this particular default that is printed out in SPSS is to carry out what is called a step-down analysis. So to perform a step-down analysis, you have to use syntax to do this. So you go to File, New, and to Syntax, and basically you can type in a title line. You don't have to, but I typically do. So I'm just going to call this step down analysis following MANOVA. You can name it anything, but put them in single quotes, and then with a period, you'll notice that title changes from red to blue. So you can see that that line is specified correctly. Then you'll start with the MANOVA command, so MANOVA, and then the names of your dependent variables. Now, the deal is that you need to prioritize those dependent variables. So, in other words, you decide on which variables receive certain types of treatments. So, and generally, the priority that's assigned follows some theoretical or logical rationale. But in the current case, I don't really have either of those. So I'm just going to identify. I'm just going to specify an ordering of importance related to the dependent variables with that limitation in mind. So I'm going to say I want to look at intrinsic motivation first. So I'm going to give that top priority, followed up by utility, which is the next independent variable, or excuse me, dependent variable from the MANOVA, and then self-efficacy as the third variable. Now, and then the next thing is then I include by, and then the name of my independent variable. And then in the parentheses, I will include the minimum and maximum values for my independent variables. So in this case, I had groups 1, 2, and 3, so I'm going to place 1 and 3 in there. And then followed up with a backslash. And by default, SPSS may try to force you into adopting one of these commands right here, but just try to get around that if you can. So then I'm going to type in print equals cell info, and then type in the parenthesis means, in parenthesis signif, and then in the parenthesis step down, then backslash, and then period. Now, just kind of studying this particular syntax, notice that, like I said, you basically are going to assign priority to your dependent variables. So essentially what's going to happen is that the step-down analysis is going to first compare the groups running a one-way ANOVA on intrinsic motivation. The second step-down test will compare the groups on perceived utility while controlling for intrinsic motivation. And then the third test will involve a comparison of the groups on self-efficacy while controlling for intrinsic motivation and perceived utility. So in other words, the first test is a one-way ANOVA comparing groups on the first variable. The second test is a one-way ANCOVA with intrinsic motivation, the dependent variable from the first analysis, being used as the covariate in the second. So then the group comparison will be on adjusted means on utility. The third comparison will involve a comparison of groups on self-efficacy while controlling for the covariates of intrinsic motivation and perceived utility, which were the dependent variables from the previous two analyses. So to run the analysis, you highlight everything and then you click on the green button, And you'll notice as you scroll down, you'll notice that you have the same basic descriptive information that we saw previously in the MANOVA output. You have also, you've got your multivariate tests, which again, here's Wilkes and so forth. There's the original value that we were talking about and the significance level. Right here, these are the between subjects tests, or the univariate ANOVAs, that I was telling you was probably not the best follow-up strategy to adopt. So as you can see, though, the test of intrinsic motivation was not significant, whereas the tests of the other two dependent variables were. But again, these tests are ignoring the intercorrelations among the dependent variables. So for the step-down test, you have intrinsic motivation, the first test being carried out. You'll notice that basically this first line right here is going to mirror what you see right here. And that is because it is a one-way ANOVA with no control variables that are being included. The next test for utility, you'll notice that the step-down F is not the same, and in fact you can see it's a little bit less right here. You'll also notice that basically for the error degrees of freedom, there's a loss of a degree of freedom because of the covariate that was included in the analysis, which was intrinsic motivation. So the p-value happened to be statistically significant, so the groups would be deemed as significantly different on perceived utility. The third test is the ANCOVA, comparing groups on self-efficacy while controlling for intrinsic motivation and perceived utility. And you'll notice that the degrees of freedom, you had a loss of degrees of freedom for the inclusion of the covariates of intrinsic motivation and perceived utility. You'll notice that the F value is clearly less in this particular case. And it turns out that the comparison was not statistically significant. So as you can see, the results here and here do not exactly match up. And again, the reason why is because here we are incorporating controls for the interrelationships among the dependent variables, whereas up here with our one-way ANOVA test, we were not. So that basically covers what the step-down analysis is. Now, another alternative as a follow-up to the significant MANOVA is to carry out discriminant analysis. And so to carry out discriminant analysis, you'll go to classify and to discriminant. Now, the thing is that what discriminant analysis basically allows you to do as a follow-up to the MANOVA is to identify those composites or linear composites of the dependent variables from the MANOVA that contributed to group separation. So in another way of putting it is basically that we are able to define the discriminant functions or define the dimensions that produce group separation on the dependent variables. So the MANOVA itself doesn't allow you to do that. All we're able to do is say, well, the groups seem to be different, but we don't know how. So the discriminant analysis is another way that we can follow this up. So in discriminant analysis, though, if we're using this as a follow-up to the MANOVA, the independent variable actually becomes the dependent variable. So we move the dependent variable over to the grouping box, and under define range, we include the minimum and maximum values on our variable, which in this case was 1 and 3, because we only had 3 groups and we'd given values of 1, 2, and 3. The predictor variables in the model were the former dependent variables in the MANOVA. So basically the discriminant analysis mathematically is really just a reverse MANOVA. So at any rate, we have our 3 predictors in the model. Under statistics, we can ask for all the means, univariate ANOVAs, boxes M. We can ask for function coefficients. We can ask for within groups correlations to get an idea about the correlations among the variables. So a lot of this stuff right here is what we saw printed out in the MANOVA results. We also can look at how well our prediction model classifies cases into their respective groups. So to do this, we can just click on compute from group sizes, since the groups are actually not equal in size, and then click on a summary table. So, in other words, discriminant analysis, can be used really for a couple of reasons. One is just to simply describe the discriminant functions that produce group separation on some grouping variable, which is what we're mainly focusing in on as a follow-up to the MANOVA. Another option is to develop a classification rule for trying to predict group membership on the grouping variable. So at any rate, so we can use this information too as a follow-up to the MANOVA. Also, we can ask for plots, we can ask for combined groups, separate groups, territorial map, which can be useful in further clarifying what's going on with the discriminant functions. The last button is the save button right here. If our goal is prediction and understanding discriminant scores and so forth, then we could click on these, and basically new variables would be saved to our SPSS data set that we can use this to study. So I'm going to go ahead and click on these so we can see what they look like. One of the notable things is that we can ask for discriminant scores, and basically these are scores on the discriminant functions, or the linear composites of the predictor variables that are producing group separation. So so this is very much akin to what we might see with factor scores in factor analysis. So we'll click on continue and OK. So in terms of our output, you'll notice that we have up here we've got our basically all this information is what we see previously with the MANOVA results. The test of equality of group means, these are just the univariate ANOVA results, a little distilled from the bigger tables that we saw previously, but they're basically the same results, comparing the groups on self-efficacy, utility, and intrinsic motivation, ignoring their intercorrelations among themselves. We have pooled within groups matrices, which just gives us an idea about what the correlation is between or among our variables. So we see self-efficacy was correlated with utility at 0.403, with intrinsic motivation at 0.197, and utility and intrinsic motivation was correlated at 0.399. If we scroll a little bit further, you'll notice that we get the homogeneity of covariance matrices tests, or boxes tests, which is basically going to be the same information as what we saw when we were requesting homogeneity tests in the context of MANOVA. So homogeneity of variance-covariance matrices assumption is an assumption related to discriminant analysis. So then that actually leads us then down to looking at the actual discriminant functions. Or basically, when we talk about discriminant functions, we're talking about linear composites of the predictor variables that are producing group separation on the individual variables. So so with discriminant functions, the thing is that the number of discriminating functions in the case of a two-group MANOVA is 1. So there's only one discriminant function that will separate the groups on our predictor variables, or kind of going back to the MANOVA with separating the groups on the dependent variables. When we have more than two groups, then essentially we follow this little rule right here in terms of deciding on the number of discriminant functions. And actually, it's less about deciding on than just knowing that this is the number of discriminant functions that would be computed when carrying out these analyses. So the number of discriminant functions equals the number of predictor variables, or the number of groups on the grouping variable minus 1. So in other words, we had, in this particular analysis, we had 3 dependent variables, and we had 3 groups. So 3 minus 1 is 2. So to take the minimum number, which is 2, that gives us 2 discriminant functions, which you see printed out right here. So we have function 1 and function 2. Now the functions, the composites, linear composites, are derived such that they are orthogonal, meaning that they are uncorrelated with each other. So each of them contributes uniquely to the overall group separation that we see on the predictor variables, or going back to the MANOVA, on the dependent variables. So you'll notice that you have eigenvalue, which is a variance index for the discriminant functions. Percent of variance is basically the percentage of between group variation on the dependent variables that's accounted for by each of the discriminant functions. So this is not the percentage of total variation in the dependent variables, but rather the percentage of between group variation. So you'll notice the first discriminant function accounts for most of the between group variation. The second discriminant function accounts for the next largest amount of variation. If we had a third function, that would account for the third largest, and so forth. So you'll notice that the cumulative percentage of between group variation would obviously be 100%. So the canonical correlation that you see right here, these are basically indexing the relationship between the discriminant functions and the grouping variable. So these will range between 0 and 1, and obviously as you get closer to 1, that reflects a stronger relationship. So we can see that the first discriminant function, or the first linear composite of predictor variables, that's producing separation on the groups, that is most highly related to, or very highly related to, the grouping variable. The second discriminant function, you can see, is much lower, and so there would be less separation on that particular function. Now, are these functions significantly related to the grouping variable? This is where these particular tests come into play. So you've got tests of Wilks lambda that are taking place. And essentially, the way that these tests operate, it operates through basically what's called a peel-off strategy. So it's peel-off. So I'll just write this in. It's kind of tough to write this in using this particular mouse, but we'll just say it uses peel-off procedure, or peel-off strategy. So in other words, what I mean by that is that the first test is actually a test of the combined effects of functions 1 and 2. So in other words, if we account, this particular test right here is accounting for the combined between group variation of functions 1 and 2 combined. Remember that functions 1 and 2 are derived to be uncorrelated. So in other words, their effect is additive. So you'll notice that the Wilks lambda value right here of 0.344 actually equals the Wilks lambda value that you saw in the MANOVA table earlier. So in other words, the Wilks lambda is for the first test is taking into account the joint effects of both of the functions. So the first test, you can see it was statistically significant. So we know that as a set, functions 1 and 2 contribute to group separation on the dependent variables. Or excuse me, with respect to the predictors. Excuse me, I'm thinking back to the MANOVA itself. The second test of the functions involves peeling off function 1, leaving only function 2 available. And so in this particular case right here, you'll notice that so the second test is a test of function 2 proper. So you can see that there was so what this means is that there was no significant relationship between function 2 and the grouping variable. So in a nutshell, what you can ascertain from this is that there's a significant relationship with function 1 and the grouping variable, whereas function 2 is unrelated. So the overall effect that we see within this test right here is only due to function 1. So this has, and you know, if we had a situation where we had 3 grouping variables, excuse me, 3 functions, in that case we would have a test of functions 1 to 3. So then we would have a test of functions 2 and 3. So in other words, we would peel off the first function, which would account for most of the between group variation, leaving just functions 2 and 3, and then we would have just a test of function 3. So that's what would happen if we happen to have 3 discriminant functions instead of 2, which is what we have right here. So given that we have, at this point, we know that we have really one discriminant function that is contributing to group separation concerning the predictor variables. So now when we scroll, we have this information, these two tables. We have the standardized canonical discriminant function coefficients and the structure matrix. And basically, I'm going to start with the structure matrix first. The structure matrix contains zero-order correlations, or Pearson's correlations, between each of the individual predictor variables and the discriminant functions in the model. So, and there are various rules of thumb for judging what constitutes a large enough loading to define that function. I've seen a couple of rules of thumb. One is, an absolute value of 0.33. Others being an absolute value of 0.30. We'll just stick with 0.33 for the time being, realizing that there are other rules of thumb. But nevertheless, the way that you interpret the structure matrix is very much like you would interpret factor loadings in the context of factor analysis. And so you can utilize the structure coefficients to determine which discriminant function the measured variable loads on highest, and use that information in order to define or name the discriminant function. So we see right here that perceived utility is loading very highly on function 1, and is loading much lower and negatively on function 2. Intrinsic motivation is loading mostly on function 1 and a very small amount on function 2. And self-efficacy is loading very highly actually on both discriminant functions. Now, adopting the loading criteria, we could use really intrinsic motivation is not meeting that criteria on either function, whereas utility and self-efficacy actually are loading on at least one of the two discriminant functions. Now the thing is that we've already determined that function 2 was not significant. So really function 2 is kind of out of the picture at this point. So if we want to name our functions, really we're not going to bother with function 2 because it's not contributing significantly to group separation with respect to the predictor variables. So if we look then at our structure matrix, we can see that function 1, or the only function that is contributing to separation on, between groups on our predictor variables, was perceived utility and self-efficacy. So I might just call this something like, let's see, what would I call this actually? Well, I'll just call it practical motivation, for lack of a better way of putting this. So we'll just call it function 1 practical motivation. Not that it has any kind of theoretical discussion in literature or anything like that. So at any rate, so practical motivation, whatever. But again, we can use the structure matrix to help name the discriminant functions. The standardized canonical discriminant function coefficients are really very much analogous to beta weights in multiple regression. So here we can actually look at each of the individual predictor variables and ascertain their relative contributions to the discriminant functions. So as you can see right here, we've got function 1, function 2. Again, really function 2 is pretty much out of the picture. If we wanted to just talk about the relative contribution, certainly self-efficacy is loading most highly on it, followed by perceived utility, and then intrinsic motivation having the lowest loading on it. But nevertheless, there's not really much point in interpreting this function because, quite frankly, it wasn't significant. So when we look at the relative contributions, we can see that perceived utility had the highest standardized canonical discriminant function coefficient, followed by self-efficacy, and then followed by intrinsic motivation. So we can use this information to help us in our naming of our discriminant function. So once again, we can still call it practical motivation. Or if we're less interested in naming the function, but we just want to talk about which variables seem to be contributing most to this discrimination between groups, then clearly perceived utility is contributing to most of the separation on the function, followed by self-efficacy. And then intrinsic motivation is really not doing much work in terms of contributing to group separation. So at any rate, now we can kind of scroll down a little bit. You'll notice that we've got canonical discriminant function coefficients, and one of the things to note is that basically these coefficients right here are used to produce discriminant scores for our functions. So this is very much analogous to the creation of factor scores in factor analysis. So basically, this is following the same general logic of a standard regression equation, where you would have the intercept plus the sum of the products of each of our coefficients for our measured variables times the values on those variables. And so each person would have a discriminant function score for each one that has been derived. So we can see right here in our output we've got discriminant function scores for the first function and for the second function. Okay, so the next chart that you see right here is functions at group centroids. So this is basically, we have essentially the group centroids are multivariate means. So basically they're means on the discriminant functions. So there'll be a mean for each group on the discriminant function. So you'll notice right here that you've got the mean for function 1, which again we're just calling it practical motivation. So for that function, the mean for plan to attend college or full-time was highest, followed by the mean for plan to attend part-time, followed by the plan not to attend at college at all. So again, if we give this function a name, which again we call practical motivation, we would say practical motivation was highest in the first group, followed by the second, and then lowest in the plan not to attend college group. Or if we want to go back and just focus on the standardized discriminant function coefficients, we can see that really the groups are being discriminated on perceived utility and academic self-efficacy. Once again, really there's not a whole lot of point in focusing in on function 2 because, quite frankly, it was not significant. So there's not really any major group or significant group separation on that function. So scrolling down, you'll notice that that we have different plots for the discriminant functions, and so you'll notice that, let's see here. So basically you have the separate groups graphs right here are just basically plots of the individual observations within each of the groups on the two discriminant functions. So you got function 1 and function 2 right here. So this is for the plan to attend college group. This full-time, this is the plan to attend part-time group, and then this is the plan not to attend group. And so this last plot right here is giving you the group centroids on each of the functions. You'll notice that essentially, as you're looking at this, you've got much more separation along the first discriminant function right here So you can see the separation between the plan not to attend group and really these two groups right here. So that's where the separation is occurring on function 1. On function 2, you can see that really there's not much in the way of vertical separation among our three groups. So that's why really it's only function 1 that is doing most of the work in terms of separating the groups. So so that's how you would interpret this particular plot. As we scroll down a little bit further, you get classification results, and you know, basically what we can ask, or what we've asked for, and I'll just kind of show you going back to the original data set here where we have our newly saved discriminant function scores and probabilities and so forth. You'll notice that over here you've got predicted group for the analysis. So the predicted groups are this information right here is being taken from or is being derived from the discriminant scores on each of the functions, and basically a probability estimate is generated, and then from that the most likely group that person would fall into is the predicted group. So you can see that for person 1, you know, this is a discriminant score for person 1 on function 1. This is a score on function 2. You can see that in terms of the probability of membership in group 1 for that person is 0.416. The predicted probability for being in group 2 for that person is 0.53, and you can see that the predicted probability of being in group 3 for that person is 0.05, or basically 5%. So based on the highest probability was for group 2, and so the predicted group membership was group 2. When you look at the second person, you can see this is the score on discriminant function 1 and 2 for that person. You have the highest probability is actually of being in group 1 out of all the three, the probabilities associated with the three groups, and so that person was categorized as falling into group 1. So that's basically how this works, and so from that information we can generate a classification table that essentially compares the actual group membership to predicted group memberships. So you can see that we have the plan to attend college, the original counts. We had 15 individuals who planned to attend college full-time. So this is what they actually said in the data. Of those 15, you can see that 6 were predicted to plan to attend college full time. So in terms of a hit, you had 6 hits on this particular category for a rate of 40% accuracy. In terms of plan to attend college part-time, you can see that you had 8 individuals here, and so this would reflect 8 misses, okay, in terms of predicted group memberships. So 8 people out of the 15 were predicted to plan to attend part-time. So we had a miss rate of about 53%. And then we had one person who planned to attend college full-time who was predicted by the model not to have that plan, for a miss rate of 6.7%. So for the second group, you can see plan to attend college part-time. So in terms of hits, we would look in the second column right here. So, and these would be plan to attend college part-time. So we had 9 hits here. So basically 9 out of the 18 people who were actually observed as planning to attend college part-time actually were predicted by the model to have that plan, for an accuracy rate of 50%. So you had 6 people who were predicted by the model to plan to attend full-time, and 3 that were predicted not to want to attend college at all. So these 2 columns right here would basically reflect misses. Then we have plan not to attend college at all, and so we had 17 out of 19 cases were correctly classified. So that was actually an accuracy rate of 89.5%. So you can see that the best classification actually pertained to those individuals who were planning not to attend college at all. So 17 of 19 were actually correctly classified, and so you had 2 misclassifications as a function of the models. So basically, as you're looking at this, you can see that the values here, and here, these are all hits. Okay, so these are all hits in terms of classification accuracy. Okay, so the long and short of it is that so these are the classification accuracy rates when it comes to those 3 categories. So again, the highest accuracy was reflected for those who plan not to attend college at all. 17 were correctly predicted by the model to not want to attend college at all. So the overall hit rate was actually 61.5%. So in other words, 61.5% of all the original observations were correctly predicted to fall into their respective groups by the model. So that's not really a very good hit rate overall. All the other off-diagonal elements that we see right here, these are all reflecting misclassifications based on the statistical model. So that basically gives us a short description of discriminant analysis. So once again, the whole point of this particular video was to give you a couple of other alternatives to a MANOVA as follow-ups, rather than just simply utilizing the default SPSS options that are given.